I just wanted to recap a bit the key point from yesterday and ask for specific questions or things that might not be clear, because today we're going to delve into slightly more complicated issues, mainly how do we model multi-level or hierarchical or mixed effects models and what it means, what it's doing to the data when we do that. Right. So the first thing, and I think it's a really key point, is that Bayesian modeling gives us a way of formalizing step by step what we know of the data and of the process that generates the data, right? Instead of trying simply to describe or assess a contrast, it's a way of actually stopping and thinking about what we know. The second is that one way of saving endless amounts of time, and I speak from experience, is that we always want to start with the simplest possible model and build up, even if we already have a good idea of the general complex model that we want to build. I had a model that took 6 weeks to run, and it wasn't fun when I discovered I had done something wrong there, right? The third point is that really specifying priors and building up the model is a way to specify our knowledge, right? It's not a belief, but it's our knowledge of the measurement scale of the problem at hand. And we obsessively check the implications of this knowledge that we formalize, but also the robustness of our estimates, right? We try to be as rigorous as we can in setting up our priors and likelihood and models that generate the data, but we also, quite aware that it's important to see how the results of our choices are robust or not to changes in our choices. And we've seen, for instance, the sensitivity to changes in prior yesterday. We discussed at least 2 levels at which we check our assumptions. The first one is the prior and posterior parameter distribution. So we plot our priors if we want to understand them, and we look at whether the posterior estimates sit well within the prior distribution or push them or haven't learned enough from the data. But especially when we get to complex models, we have lots of priors, and it's non-intuitive how they correlate with each other and how they interact with each other in terms of the outcome scales. And especially when we get to more complex models, let's say reinforcement learning, we might not have as good an intuition as to what temperature might mean, right? And that's why we have a second level at which we check our models. That's the predicted outcomes, right? Where we combine all the likelihood and prior specifications that we've done, and we check how it looks like, right? And we've seen that in the prior and posterior predictive checks. I think to keep in mind that these are 2 separate levels of checks, right? It's quite important. And what I wanted to ask you at this point is that seeing the work that we do to define the priors, seeing the way we motivate the priors that we build, does that make you a bit more comfortable with the idea of priors, right? With, of course, the awareness that you've only started setting priors, at least within this course, in very simple models. So it takes a while to build a good intuition, but at least are you a bit more comfortable with the idea that priors is not just a subjective matter? Okay, I see a couple of nods and I see a chat. Let's see if, oh, yes. Micah is saying, just for your information, for those who may not know, temperature reinforcement learning models is usually something like a slope parameter on the decision function, and it determines how sensitive choice is to a reward. In other sense, it's a way of saying that the model, can learn a lot or a little from the feedback that you're getting, right? And I use that example because it's a parameter that's far from the data that we observe, right? And therefore, while we can get an easy grasp on the actual data that we produce through the experiment, it's harder, unless you have a lot of experience, to have a good intuition for how temperature should be, because it's a parameter that's latent, that's hidden below the data, right? Okay. So are there questions on the progression that we had so far, right? We define articulation, the articulation space of the vowels as a Gaussian, right? We built our priors for the mean and the standard deviation. And then we moved into a more interesting question that was, do we see a systematic difference between the articulation space in infant-directed speech and adult-directed speech, right? So we built a linear model with a dichotomous predictor, or if you want, a t-test, right? We also saw that we are not constrained to only condition the mean to register, saying that only the mean articulation space will change, but we can also condition the sigma on the register, right? We can say that also the variance, so how variable people are in the way they produce these vowels, might change according to the condition, right? According to the register, which is something that is very common, as we said, for instance, in psychiatry studies where the patient populations tend to be more heterogeneous than the control populations, right? If you remember the famous quotation, right? All happy families are happy in the same ways. All unhappy families are unhappy in their own ways, right? Okay, so